All right. Uh, Good evening, everyone. I am Ganesh, and thanks for joining. We have three people here: Shyam, Krishna Kumar, and Avinash Sivam. Thanks for joining. Um, so today, what we are going to do is we are going to solve some fin problems because that was week four's content, and we'll solve like two problems, and the floor will be open for your questions if you have any. So before I get into today's topic, do you want any urgent matters to be discussed? If you want, you can let me know. If not, we can start with today's topic. All right, I'm hoping there is no questions from your side. Uh, so uh, maybe we will start with solving some problems, and you are free. Feel free to stop me anytime in between if you have any doubts. And yeah, hopefully this would be helpful for your assignment 4, I guess. Okay. So what we did in week 4, especially in the class, if you look at it, we studied about heat transfer from an extended surface, or heat conduction basically from an extended surface. And uh, or you can, the extended surface, you can also tell these are fins. Okay, these are to improve the heat transfer uh, from your devices. Okay, these are the fins. So we started with something called this rectangular fin. So basically we have this, we add additional material in such a way to increase the surface area for convection, and that will help to improve the heat transfer from this device. So this can be anything. So this can be either a furnace wall, or even your engines. For example, your two-wheelers engines, if you look at it, there will be a lot of fins attached to it. Okay, so it will be, it's just a piston cylinder going up and down. It's cylindrical engine, and surrounded by it there will be a lot of aluminum fins attached to it. And it is also, for various devices, we'll be able to see these kinds of fins. Okay, and if we have such a fin, there is an additional convection, convective heat transfer that is going to happen on the surface of the fin, which we are going to take into account in our heat transfer analysis. That is what we did in the week 4. So initially we started with something called rectangular fin, or in general we derive this equation. This is without heat generation, and we simplify telling that k is constant, and then area is also constant for a rectangular fin along the x direction, along the direction in which you are applying. So these are all 1D assumptions. So when I draw this 3D, doesn't mean I'm performing a 3D heat transfer analysis, but I'm only I'm assuming the heat transfer on the other directions to be heat conduction basically on the other directions to be negligible, and I'm only assuming heat is transferring along the x direction, because this is at high temperature, and overall the ambient is at low temperature. So heat is supposed to travel in the certain direction where the temperature difference is there, and that direction is x for us. Okay, so this is a one-dimensional heat conduction equation with the convective terms here, and you see here it's not a, it's p, perimeter of the uh, fin. Okay, and we performed this analysis and we got this general solution, and we implemented boundary conditions. So base temperature is known. Our base temperature is one of the boundary condition. So using that we got some equation for the constants, and there are three different kinds of boundary conditions that we saw. One is very long fin, and another is finite length of a fin. Let's say I very long fin means infinite length. I'm going to extend it till to a length such that the temperature of the tip will be equal to the ambient T infinity temperature. Okay, so that could be used as one boundary conditions, and that if you use that, this would be your total heat transfer from the fin. And similarly there are, but that is not practical, so we have different sets of boundary conditions. The other boundary condition is finite length of a fin. Usually we have finite length of the fin, but we are going to assume that the tip is insulated, which means the tip is not going to perform any appreciable heat loss. You can also say the tip is insulated, means there is no heat loss across the tip, but the same thing can be approximated to tip where the heat loss is very less compared to whatever the heat loss that is happening on the fin. Okay, so if that is the case, then this is how your solution will look like. And this is more general, more practical relevant case where you have uh, finite length of fin and you have a convective heat loss condition at the tip. Okay, which gives the so this is most practical boundary condition that you can apply. And if you use this boundary condition, then your solution becomes somewhat complicated, and hence your heat transfer from your fin also becomes a little bit complicated. But there are a lot of readily available graphs and plots, and also calculations you can easily, or tabulations which you can usually use to perform such kind of analysis. You no need to really need to remember these equations. Okay, and next is fin efficiency. We also saw there are two performance parameters you can say for fin. How will you quantify the performance of fin, right? So that is based on fin efficiency and fin effectiveness. In fin efficiency, what are we telling is, let's say I have a fin, and if it talks about the thermal conductivity or the conductive heat transfer inside the fin. Okay, so let's say if I have uh, very high thermal conductive uh, let's say if my fin is made of very high thermal conductivity material, then I won't see any appreciable loss of temperature along this fin, along the fin, and then that would be most efficient. If I see appreciable loss of temperature along this fin, then it would be less efficient. Okay, so that is what the fin efficiency talks about. It talks about actual rate of heat transfer from the fin divided by if the entire fin is at base temperature. If there is no, if there is no conductive resistance, or if there is very least conductive resistance. Least conductive resistance will be the case when you have very high thermal conductivity. So which means if you have a very high thermal conductivity, or K tends to infinity, then the entire temperature in the temperature of the fin would be entirely TB, base temperature. Okay, if the entire fin is at base temperature, what would be the heat transfer? That would be the maximum heat transfer. If that maximum heat transfer is in the denominator and the actual heat transfer, if you put it in the numerator, then that is what we call it fin efficiency. Okay, and the next one is fin effectiveness. This actually justifies whether we need a fin or not. So let's say if I have fin, what is the heat loss I'm going to, what is the heat transfer, total heat transfer I'm going to get compared to when I don't have any fin. Okay, so Q with fin and Q without fin. So whenever you are designing, let's say fins, whether you need a fin for that system, if you want to analyze that part, then you have to go and find out what would be the effectiveness of a fin. Okay, and when you have the fin, how efficient that fin, if you want to know, then you have to quantify fin efficiency. Okay, I hope this so I hope the difference between these two parameters are clear for you. If not, please let me know. I will be happy to describe you again. Okay, and then finally we wrote this most general equation which you can apply to any set of one-dimensional fin problems. Okay, so if you know this equation, you can just substitute all the areas. If a area is variable also, it's fine. K is variable, it's fine. If you have heat generation, then also it's taken into account. So everything is taken into account here. So if you have a lot of complications in your system, then you can use this general equation. Of course, it's for 1D analysis, and you can solve this equation and you can get the temperature field and heat transfer and everything. Okay, so this is what we saw in the week 4. This is a quick recap that I did for week 4 for you guys. And we also saw 2D steady state conduction, heat conduction, but it is not fully complete. We are yet to understand some more we need to get full understanding by if you go through week 5, you will get the full understanding. So I'm not going to go through 2D steady state heat conduction today. Maybe I will go through in the next week. Okay. So this is what we did. We studied heat transfer from extended surface, and we also did 2D steady state heat conduction, but it is in progress. So we will study more in the next week, week 5. Okay. So um, in the class we solved, I guess, so rectangular fin. Professor Som solved rectangular fins. Here I chose spin fin and annular fin, and I think this would be very helpful for your assignment also, because in assignments are also they are using pin fins and annular fins. Okay. So one question is on pin fins and the another question is on annular fins. Okay. Any questions till now? All right. If there are no questions, I will move forward. Let's go through the question one first. So the question one talks about a pin fin of uniform cross-sectional area is fabricated of an aluminum alloy. Okay, so the fin's material is aluminum alloy with the thermal conductivity is given. The fin diameter and fin length is 4 mm. So it's a pin fin, which means it's a cylindrical fin attached to a surface, and its diameter and the length is given, which is 4 mm and 35 mm respectively. Okay, and the fin is exposed to convective conditions characterized by uh, H equal to 220 watt per meter square Kelvin. So the convective heat transfer coefficient on the surface of the fin uh, is 220 watt per meter square Kelvin. It is reported that fin efficiency is 0.65. Okay, so they have already given fin efficiency. They have already uh, uh, performed this calculation. So we have to find out, determine. Sorry, there's no fin efficiency. Determine the fin effectiveness. So we have to find out what is the fin effectiveness. Okay. Uh, Wait a minute. I guess we can actually find out fin efficiency. Yeah, I modified the question a bit, but I forgot to remove that statement. Anyway, fin efficiency is not 65% for this, so uh, we are going to calculate. So we have to calculate both fin efficiency and effectiveness. Okay, so let me draw it so that it will be clear for you guys. So we have some surface, and then we have this fin attached to it. Okay, and it's a this is a circular fin. Okay, so maybe I will draw a center line to it so that it will be easy to understand. So it's a circular fin. I'm drawing only cut section of it, and the diameter here is given to be 4 mm. Okay, 4 mm, and the length of this fin is given as 35 mm. Now the thermal conductivity, this is an aluminum alloy. Okay, so we know at this point the temperature is base temperature, and then you have convective heat transfer everywhere, and we are assuming fin to be insulated. We are assuming fin to be insulated, or there is not much of a heat loss from the fin tip. Okay, the fin tip is to be insulated, and what else is given? You have thermal conductivity to be 160 watt per meter Kelvin, and you have H to be 220 watts per meter square Kelvin. Now we are asked to find, one is efficiency of the fin and another one is effectiveness of the fin. Okay, what would be the efficiency and what would be the effectiveness? So remember that there is no temperature data given, so which means without the data we can actually find out fin efficiency and effectiveness. Okay, all right, any idea you guys have? First thing is we need to find out fin efficiency. So what is fin efficiency? So if you go back to the, so as I said, is the actual rate of heat transfer, or Q fin divided by Q when the entire fin is at base temperature. Theta B. Okay, maybe we can give this as this to be QF divided by QFB. Okay, QFB is when you have, or Q max. QFB is Q max. This is the maximum heat transfer that you can get from the fin. Now, give me a minute. Okay. Yeah. All right. So now we need to find this efficiency of the fin, and this is it's a simple uh, fin. So for which we already did a constant area, constant cross-sectional area fin, for which we already did in our class. We derived the efficiency of the fin formula. So if you go back, so this was our QA when it is a long fin. When fin tip is insulated, then our efficiency is tan h ml by tan hyperbolic ml by ml. Okay. So if you go back, so what does it mean? So you have a finite length of fin with an insulated tip. So for which the total heat transfer rate is root of HPKA tan HML by uh, TB minus T infinity. And what is the uh, QB? QB is HPL theta V. So uh, when you divide this by HPL theta B, this is nothing but theta B. This gets cancelled, and this HP and root of HPKA becomes m. Okay, so if you do it carefully, it becomes 1 by m. So this is nothing but, sorry, so this is nothing but tan HML by ml. So this we didn't explicitly derive in the class, but professor wrote it in the board if you paid attention. Okay, so we can use that information. What is it? Efficiency of fin is nothing but tan hyperbolic ml divided by, sorry, divided by m times L. Okay, so we already know what are m and L. M is nothing but square root of HP by KA, and P is the parameter, A is the area of cross section of the fin. Okay, now this is where you should be a little bit careful. What should be the perimeter and what should be the AC or area of cross section? You should be very careful. Once you identify that, the entire process is very simple. Okay, so let's first try to find out what is M. So in this case, so how does it really look? So if I want to draw it in 3D, it's going to be like this. So this is the fin and this is the surface. Okay. Okay. So now, what would be the perimeter? So perimeter is the surface across which the convection is happening, right? So this is the surface across which the convection is happening. If you remember, if you go back to the notes, we saw what are the, so there are like four surfaces across which the convection is happening. This is one, and backside, and then at the bottom, right? Four surfaces across which the convection is happening, and that is the perimeter. Okay. All right. So here that perimeter is going to be perimeter of the circle. So if we write that down separately, so this is going to be pi times d. Okay. This is diameter d. So perimeter is going to be pi times d, and area of cross section we already know it's a pin fin or circular pin fin. So it's going to be area of the circle, which is going to be pi by 4 d square. So you can substitute them here, h pi d by k into pi by 4 d square. So you can make this simplification, which comes out to be 4h by kp. Okay. So we know, sorry, kd. We know diameter, we know h, we know k. We can directly find out m, which would be 4 times h is 220 divided by 160, I guess, k, 160, and diameter is 4 mm. Is 4 into 10 power minus 3, and there is a square root. So if you perform this calculation, how much would m come out to be? So if you guys find out, please let me know. So my calculation says that m is 37.1. Okay. And this m also has units. Okay. So if you do it, maybe it's not very much important, but it's better to write the units. So watt per meter square Kelvin, and perimeter is meter divided by watt per meter Kelvin into meter square. So watt Kelvin, these things goes away, meter, this goes away, and this also goes away. What is remaining? So you have meter square, 1 by meter square, and square root is 1 by meter, so it will be meter inverse. Okay, this is m, and L, we know the L. L is just the length of the fin. This is L. So we can directly find efficiency of the fin. So efficiency of the fin is going to be tan hyperbolic 37.1 into L is 35 mm, 35 into 10 power minus 3. So you can see m is meter inverse and L is meter, so it gets cancelled, so it becomes a non-dimensional inside the tan hyperbolic. And that is necessary because tan hyperbolic, you cannot write units in tan hyperbolic, right? The same with exponential. Whatever the expressions that you have inside an exponential usually will not have units, which means that will be a non-dimensional group. And then divided by ml. So if you perform this calculation, So you may need to use scientific calculator for this, because hyperbolic functions are available only in scientific calculator. So if I perform this calculation, if you have, please let me know what is the answer for this. Okay. So I'm getting something like 0.66333. So maybe you can write this as 66.33%. So this is the efficiency of the fin. Okay. This is how you calculate the efficiency of the fin. So here we used the uh, uh, a derived formula, which is tan hyperbolic ml by ml. You can also start from first and you can do the derivation by yourself, but to save time I started with this. Okay. And this is because we already have the formula. Okay. And this is for insulated tip, this is not for convective tip. Okay. If this is a convective tip, then your formula will change. Basically this will not be tan hyperbolic ml. Instead it will have sin hyperbolic ml plus h by mk cos hyperbolic ml. All these things, all these complications will be there. Okay. You should apply appropriate formulas for this. All right. The second one is fin effectiveness. Fin effectiveness. Now, if you want to find fin effectiveness, let's first write down the equation, or um, definition of fin effectiveness. Fin effectiveness is nothing but Q with fin divided by Q without fin. When you do not have any fin, what is the heat transfer that you are going to get? That will be Q without fin. And when you have fin, what is the total heat transfer? That's what Q fin is. So, how do we find Q fin now? We already know the efficiency. So from here you can write Q fin to be, we already know the efficiency of the fin. So you can write Q fin to be efficiency of the fin times the QFB, right? Maximum QF. Okay. Or actually you can find Q fin, because uh, we already have derived the formula. So this is the formula, actual heat transfer from the fin. Only thing is TP by T infinity we don't know, but it will be numerator and denominator, so you can cancel it. So you can actually do this also, root of HP by Ka into tan H ml. Okay, but let's see where this leads to. This might lead to an interesting result. So this would be H times area of the entire fin times theta b, right? This will be Q fin when the entire fin is at base temperature. That is this part. When you multiply that with efficiency, you will get the actual heat transfer rate from the fin. Okay. Now, what would be the Q without fin? Q without fin would be simply the surface area. This is the surface area. Okay, this is the surface area which is been exposed. Now it will be simply exposed to convective conditions. That's all. So all the surface area is now lost. If there is no fin, there is no fin. So you will have only this surface area. You just need to find heat transfer through that surface area. How will you find that? It is going to be simply H times area of cross section of the fin. Right, this is a cross section of the fin, or area of cross section of the base, and multiplied by theta b. Now let's just substitute this. This is going to be efficiency of the fin times H A fin theta b divided by H A C theta b. So this theta b cancel, H cancels. So this simply boils down to how much increase in area that you are getting when you add a fin. Of course, you have a multiplicative factor, which is efficiency of the fin. So please understand, This gives multiple perspective of same parameter that we are talking. Okay. Now area of the fin is going to be, what is the area of the fin? It's going to be this entire area, this entire surface area plus this surface area if the fin is not insulated, but since it is insulated there is no heat transfer, so it's going to be this entire surface area, or perimeter times here. So let's write that down. So efficiency of the fin is going to be perimeter, which is 2 pi, or you can write pi d times, pi d is the perimeter times the length, divided by uh, pi by 4 d square. So now you can cancel this pi also, d. So this becomes 4 times efficiency of the fin L divided by D. Okay. So what this exactly says is, just because adding a fin will not necessarily lead to an increase in effectiveness or increase in heat transfer, your efficiency also should be taken into account. That's what I'm trying to say. So if you just add a fin, and let's say if you do not have this term, then which means it just gives you a condition that area of fin is always greater than area of cross section. That is going to be sure, for sure, right? So now just because adding the area doesn't necessarily mean you have higher heat transfer. You also have something called efficiency of fin, which is also a parameter, which is a function of thermal conductivity of the fin material. Okay, which is a function of thermal conductivity of the fin material. So uh, you have to take both of these into account. That's what I'm trying to say. Okay, so now you can calculate this. How much is this coming out to be? 4 into 0.6633 times length. The length is going to be, okay, sorry, length is going to be 0.035 divided by diameter 0.004. So if you perform this calculation, uh, so I am getting effectiveness something like 23.2. So please let me know if there is some error in my calculation, but this is what I'm getting. And also you can see the numbers is like it should be greater than 1, and usually you will justify only if it is greater than 2 or 3, because you want higher heat transfer. The factor 2 would be to consider all the practical implications, right? So all these things if you take into account, uh, if you have effectiveness greater than 2, then it is most justifiable to add a fin. If not, it is not justifiable to add a fin. Okay. All right. So this is what the first question is about. I hope it's clear. It's just a simple pin fin problem. Now we have a slightly complicated. It's not that complicated. In fin problems, only thing you need to remember is you need to understand which area and perimeter we should consider. Other than that, there is nothing complicated in it. Although in the lectures we would have derived a big complicated formulas, but uh, at the end of the day, it boils down to our understanding about which perimeter and area is responsible and how I should use them in the the formulas that we have. Okay. Now, the second question talks about annular aluminum fins of a rectangular profile are attached to a circular tube. So it's an annular film. Annular film means it's going to be circular, but the profile is rectangular. So the cross section, if you take, it will be rectangular in cross section basically, which means it's a disc kind of fin. Okay, attached to a circular tube having an outside diameter of 50 mm and an outside surface temperature of 200 degrees Celsius. The fins are 4 mm thick and 15 mm long. The 50 mm long is in the radial direction. The system is in ambient air at a temperature of 20 degrees Celsius, and the surface convective coefficient is 40 meters square, 40 meters square, 40 40 watts per meter square Kelvin. Okay. Now, if the fin efficiency is 97 percentage, which means we no need to worry about whether the tip is insulated or not. Here we can assume it to be, it is convective, uh, more practical application you can assume. So the fin efficiency is given 97 percentage, so there's no problem. It will simplify our calculation, so we no need to remember the big heat transfer from the fin formulas. We can just use fin efficiency expression to find the heat transfer through the fin. What is the effectiveness of the fin? We have to find the effectiveness, and they are asking if there are 25 such fins per meter of the tube length. So the tube is like, tube's diameter is 50 mm, and let's say if you have 1 meter tube, and in that 1 meter if I have 125 fins like this, then what is the total rate of heat transfer per unit length of the tube is what they are asking. Okay, so first for that we need to find what is the heat transfer through one fin, and then we can find what is the heat transfer through the entire circular tube when it has fins, 125 fins. Okay, I hope this is clear. Maybe I will draw the diagram so that it will be even more clear. So you have, since it's a circular, I'm again going to draw a center line. Okay, and then this is your circular tube. This is the radius. So diameter is 50 mm, so I am going to write this is going to be 25 mm. Okay, this is a circular tube, and its surface temperature is also given. So the surface temperature, or you can call it TB or TS, it's going to be 200 degree centigrade. Now we have a fin which is protruding out like this. Okay, and so the length of this fin is 15 mm, and the thickness of this fin 4 mm. So the terminologies that they give in the question itself will give you an idea how this fin, even if they didn't provide you the diagram of the fin, using the terminologies you can actually find out what is this, what is the profile of this fin. So for example, here this entire thing is, if you have to revolve it around this dash line. Okay, so this entire, this thing, if you have to revolve it around this dash line, this will be a circular profile. This will be a circular tube. So basically I'm trying to say, um, how would I draw this? So this is the tube, and then tube is extending in the z direction. Okay, and you have a fin of thickness. Well, my drawing is very bad, but this entire region is the fin. Okay, and this is the tube. So inside anything can happen. Maybe water is flowing in, maybe this is a circular pipe, we don't know about that, but the surface of this is going to be 200 degrees Celsius, and the T infinity is 20 degrees Celsius. That's what it means. So maybe I'll write it here, 20 degrees Celsius. So this is basically a circular fin. That's and also they call it annular fin for this. All right, this is just for your understanding. I draw this very bad figure. So, and what are the other parameters given? Convective heat transfer coefficient is given, which is 40 watts per meter square Kelvin, and the base temperature, and okay, all these two are given. It's an aluminum fin. So I think K they forgot to give. It's going to be same as previous. R, okay. So K is something. Let's see. We may not need also having outside diameter, outer surface. All right, I think everything is covered. So only thing is efficiency of the fin is given. Efficiency of the fin is 97%. Okay, which means it's a very high thermal conductivity material the fin is made of. All right. If this is the case, what is the effectiveness of the fin? That is the first one we need to find out. What is the effectiveness of the fin? And the second is, let's say I have the number of fins is 125. Then what is the total heat transfer from this entire circular tube with fin? What they are asking. All right, let's try to find out. First one is fin effectiveness. So fin effectiveness is nothing but we already know it's total heat transfer rate of the fin divided by when you do not have any fin. Without fin, what is the heat transfer rate? So now we actually don't know both of them. We don't know what is the heat transfer rate of the fin. So that I think we have to calculate from the efficiency of the fin. So efficiency of the fin is given, which is going to be Q of fin divided by Q of fin when your entire fin is at base temperature TB. So which you can write this as Q of fin. Q of fin is the actual heat transfer rate of the fin. Okay, and Q max is nothing but H times area of the fin times theta b. Okay, now H is given, area of the fin we have to find out because all the dimensions are given, and theta b is also given. Theta b, TB is 200 degrees Celsius and T infinity is 20 degrees Celsius. Theta b is TB minus T infinity. All right, now we can write Q fin. So our aim is to find Q fin and we will substitute it here. We will substitute it here to find the effectiveness of the fin. Okay, that's the logic. So Q fin is nothing but efficiency of the fin times H times area of the fin times theta b. So this is 0.97, H is 40, theta b is 200 minus 20. Now only question is what is the area of the fin? That is what we are interested in. Okay, if we understood the area of the fin, we can easily find out uh, the remaining answer. So what would be the area of the fin? You have surface area here, here and here. Okay, this is the total surface area that is uh, in this is 2D, so you have to revolve this surface area along the center line, which means you need to multiply it with uh, pi, right? So once you know this, you just multiply with 2 pi, you will end up having the entire surface area. So here this is so this is nothing but you have a circle and you have an inner circle, and then the surface area of the fin, this circular surface area, concentric circular, and then multiply by 2 times the uh, uh, so basically it's a disk. Maybe I will draw here for better clarity. So I am drawing a little elliptical here. Oh, I don't know how to draw this. So this is the top view of the fin. Okay, so this is a circular tube whose diameter is 50 mm, and this is the length that they are given, which is 15 mm. 15 mm, and this entire surface area is available for this entire surface area is the fin surface area. And similarly you have the surface area at the bottom also. This is one, this is at the bottom, and then you have the what do you call, the perimeter, or curved surface area of this disc. Okay, this disc, so you have curved surface area of this disc. So probably I will draw. So this is the thickness. I guess the thickness is 4 mm. So now if I want to write area of the fin, okay, let's give this to be R1, and let's call this to be R2, and let's call this as T. Now if we draw this, area of the fin is going to be pi times R2 square minus R1 square multiplied by 2, because it's top and bottom. Okay, this is 1, top and bottom, and then you have these surface areas, which is also available for convection. That is going to be plus 2 pi R2 into T. Okay, this is your total area of the fin. All right, if you are clear on this, you can find out what is R2 is going to be 25 plus 15, which is 40 mm, and 25 plus 15 is equal to 40 mm, and R1 is 25 mm, and T is 4 mm. So once you know this, you can easily find out A fin. So area of the fin is going to be pi into 0.04 square minus 0.025 square times 2 plus 2 pi into 0.04 times 0.00. Okay. If you perform this calculation, what is the area that you're getting? So I am getting some area, something like 7.1314 10 power minus 3. I'm prone to make mistakes, so please calculate once by yourself. Alright, let's say if I substitute all the numbers, what would happen? 0.97 times 40 times 180 times 7.1314 times 10 power minus 3. So this corresponds to I'm getting something like 49.8 watts. This is the amount of heat transfer that we get from the fin. Okay, now we found what is fin. Now Q without fin. So let's say if I do not have that fin, that is going to be easy to calculate, right? If I do not have that fin, I am going to have what I'm going to have. I'm going to have just a circular tube, which is of 25 mm, and the area which is covered by this 4 mm thickness is the only area available for the evaporation. Sorry, for the convection. Okay, so basically I'm trying to say this 4 mm times this 25 mm, and this is the only area available for the evaporation when you do not have a fin. Okay, So this is going to be h times area of the cross section, or in this case without fin, times theta b, which is going to be 40 times 180. Before that, area of the fin is 2 pi into 0.025 into t is 0.004 times 180. Okay, so it's going to be 2 pi r1 t, which gives a without fin to be 2 pi r1 t. That is the area without fin. All right, now if you calculate this number, it's going to be 2 pi 0.025 0.004 40. So I'm getting something like 4.523 watts. So this is the amount of heat transfer you will get when you do not have a fin. When you have fin, you will get something like 49.8 watts. Now what you do, you just divide them. The effectiveness of the fin is going to be 49.8 divided by 4.523. 49.8 divided by 4.523, which is going to be 11. So the effectiveness of the fin is 11. Alright, so this is the first part of the problem. The second part is when you have 125 such fins in your tube, then what would be the total heat transfer? Okay. Now this is your tube and you have these fins aligned like this. And let's say this is like 1 meter where you have 125 such fins. Now what would be the total heat transfer? Okay. So which means the total heat transfer is going to be Q number of fins times the total Q fin, which means number of fins plus heat transfer from single fin plus Q from the unfinned surface. Unfinned surface. So we already know Q fin, we know N fin, we just need to find Q from unfinned surface. The unfinned surface Q is going to be simply the total surface area. So H into A unfinned surface times theta B, which is going to be A unfinned surface is going to be total surface area of the fin, total surface area of the tube. Okay, which will be pi r1 2 pi r1 into L minus number of fin times 2 pi r1 into T. So you are just subtracting those areas where the fin is present. Now if you do this calculation, it's going to be 2 pi 2 pi 2 pi is common, 2 pi r1 is common, maybe I can take them out, into L minus n fin times T. L is 1 meter and n fin is 125 times let me write that down, 2 pi r1 1 minus 125 times 0.004. So I think this is comes out to be which is going to be simply pi times 0.025, and that is 0.0785 meter square. This is the area which is not finned, and that is available for convection. So let's say if I substitute them here, Q unfinned surface, this is going to be simply H is 40 times area of the unfinned surface, which is 0.785, which we just calculated, multiplied by theta b, which is 200 minus 20, 180. So this corresponds to some 565.5 watts. This is the amount of heat transfer from an unfinned surface. So let's calculate the total heat transfer. It's going to be n fin, which is 125, and we also found out in a single fin what is the heat transfer. That is going to be this one, 49.8 watts, 49.8 plus Q unfinned surface is 565.5 watts. So this corresponds to, it will give an idea of what is happening when you have a fin. So you have 6225 watts of heat transfer when you have fin. However, in the unfinned surface we have very less heat transfer. Okay, so adding a fin is will enhance your heat to a very high extent. So total comes out to be 6790.5, which is like 6.79 kilowatts. These are all per meter. Okay, so please note that. So we assumed it to be 1 meter in the calculation. So if I want to remove that assumption, then I will just divide it by meter. Maybe I will write it down here for 1 meter tube length. Okay, this is your total heat transfer. In that, most of them is coming from the fin surface. So if you do not have fin surface, you are going to have like only 10% of this heat transfer, and that is what exactly the effectiveness says. Effectiveness says 11, which means basically this unfinned surface is going to be 11 times lower than the finned surface, or the fin heat transfer is going to be 11 times more, roughly, when you do not have a fin. Okay, so this is the second part that we are asked to calculate in this problem. I hope this problem is also clear. Only thing you need to understand how this fin is constructed, and uh, you need to understand what is efficiency and effectiveness of the fin, and you need to apply your logic accordingly. That's all. So it's not like complicated topic. Okay, any questions you have till now? We have solved 2 problems today. I think this is more than sufficient for you to understand the assignment and solve them. All right. If there are no more questions, maybe uh, I will be here till 9 o'clock. So if you have any questions, you can ask. If there are no more questions, then we can meet on next week, same time. Okay. And we will look into 2D steady state heat conduction problems, or transient heat analysis based on your assignment problems. Okay. 2D, I think steady state heat conduction usually they will not give, because it requires you to use maybe computers or so. So probably transient analysis we will look into it. Okay. All right. Thanks for attending. Thanks, Krishna Kumar. Thanks, Avinash Shivam. If you have any questions, feel free to stay back and ask. If not, we'll meet on next class. Okay. Thank you, Avinash. No problem.